Hi everyone. I hope I am audible. Okay, fine. So welcome to the first live session. We will mostly take the doubts that you have posted on the portal, and then if we'll have time, we'll see some more questions if we can take. Okay, so yeah, so the first question that that came was, what difference will it make if we do not clean a substrate? Okay, and we start fabrication without cleaning the substrate. Okay, if you remember, I have mentioned that there are number of contaminants that is available on a wafer surface, and those contamination comes from the various processes through which a wafer goes. Okay, so some of the contamination is shown over here. Let me take the laser pointer. Okay, you have first of all native oxide of thickness less than 10 nanometer available on a silicon wafer, and that is a property of your wafer itself to get oxidized. And if you remember, we have discussed that that's why silicon is most suitable material for the microelectronics and the silicon or semiconductor in the industry. Okay, however, it has some demerit also, like the formation of this native oxide is not a good sign for a fresh fabrication. Okay, so we have to, of course, remove this native oxide also to have a thermally grown oxide which is grown in a controllable manner. Okay, then other kind of impurity that is available on a wafer is the form of certain organic materials like some paints, some dye, or some oil. Okay, these kind of materials are available because of handling and other issues. Okay, then you have a number of inorganic materials, number of cations and anions at the silicon surface, and then along with this you have various adsorbed molecules. Okay, this adsorbed molecules is of course donated by the ambient in which this wafer is kept. Okay, and along with this you have some bigger particles also in the form of dust and other things. Okay, so all these particles, if you do not clean, although they looks like a small particle on a bigger wafer, okay, but please remember that the structure that you are going to fabricate is a small structure. Okay, so just see one example shown over here. Okay, this is a 10 micron scale. Okay, on which certain thing is patterned. You can see something it has been patterned nicely in this half, and then you have some particles over here. Okay, these particles, if you see, is damaging number of devices which is beneath it. Okay. Similarly, here also you can see that there is a big hair which is falling on a patterned substrate. Okay, so the devices which are beneath this hair is already damaged. Okay, and all these devices which have been fabricated on this wafer are not mostly the individual components. Okay, they are also interacting with each other, and the wafers are stacked in a manner like the concept of local interconnects and global interconnects, right? So you have number of wafers stacked in a fabrication, and if these wafers are not only communicated on the transistors which are placed on this particular wafer, but it is also communicating with the transistors which are fabricated on the other substrate also. Okay, so all this communication is gone once you have this particle on the substrate. Okay, before you fabricate this device, if this is available, that particular area remains unutilized. Okay, so you are not able to utilize that area properly, and you cannot have a proper fabrication or proper orientation of the devices on the wafer. Okay. Along with this, there are many complications associated with the device fabrication steps also, like say lift off. Okay. So if you do not have a clean wafer, and if you metallize it and you try to lift off, the lift off will not be proper, and you may face a lot of issues in that. Okay. So we'll also try to understand this with an example. Like consider a human hair. Human hair typically ranges in diameter from 17 to 181 micron. The average length of hair on a person's head can, of course, vary greatly depending on the person's choice. But usually it ranges from 10 centimeter to around 100 centimeter. So consider a hair of this dimension. Okay. Now, consider a case that you have a 4-inch silicon wafer that you want to pattern. Considering that there is a perfect packing without any loss, which is arising because you want to give space between two devices to have a nice segregation of these devices after dicing. Okay, I'm not considering any defects on this wafer, and I'm not considering any circuit design constraint. So if you, in that case, you can pattern of around 8.1 into 10 power 11 transistors, or if you are considering a sensor of this particular size, let's consider it as a sensor. So if you have a sensor of size 100 nanometer by 100 nanometer, you can pattern ideally of the order of 8.1 into 10 power 11 this kind of sensors on a 4-inch silicon wafer. Okay. Now, consider that human hair of a diameter, say 181 micron, falls on the wafer. It covers and potentially damage around 25 lakh of sensor or the transistor, okay, which has a minimum feature size of 100 nanometer. So you can think of the damage caused by a small hair of this particular dimension. Okay, and now you can think about the damage caused by say dust particle or other microparticles. Okay, so the damage caused is enormous in this, and that's why you have to clean your wafer. Okay. Then another question was, are sensors and actuators are a subset of the transducer? This question is wrongly written over here. We'll take it after some time. Okay. So I hope that this question on what difference will it make if we do not clean our substrate is pretty clear to you, and you can I hope that you understood the matter that cleaning the wafer is very much essential, so that you get the proper lift off done, you get the proper fabrication done on the wafer, and it doesn't damage any other device that you have on a wafer. Okay, so let's take the second question, which was, our sensors and actuators are a subset of transducers. Okay, to understand this question, what we have to do is we have to go back to our slide where we talked about all this transducer, sensor, and actuator. Okay, so if you remember, we defined a transducer as a device which converts any useful energy to another form of energy. Okay, like say in one form, say one form is say heat energy. Okay, and it converts that into mechanical energy. Okay, similarly you can think of any say chemical energy, and the transducer convert that into say heat energy. Okay, so this is a definition of a transducer. Okay, then we defined a sensor which uses a concept of conversion of any useful energy to electrical energy, right? So what you are doing here is you are basically transforming, say for example, say chemical energy to electrical energy. heat energy to electrical energy, mechanical energy to electrical energy. So what you are essentially doing is you are converting one form of energy to another form of energy, but the another form of course, this sensor is a subset of transducer, because what you are essentially doing is you are converting one useful form of energy to another form of energy. Transducer do not define this another form of energy. However, a sensor is defining that, right? So in the sensor, the output form of energy is fixed, which is electrical in nature. Okay, so then let's see the actuator. The example that we have taken for actuator was, if you remember, of an electrical motor. Okay, so what it is doing is it is converting the electrical energy to another form of energy. Okay, so if you see, the input to the actuator is fixed, right? Particularly in the form of energy that it takes. So you have electrical energy which is being supplied to an actuator, and it converts to that energy, electrical energy given to it, to another form of energy. And that another form of energy can be, say, a mechanical energy. It can be simply a heat energy. Okay, it can be, say, for example, chemical energy. Okay, so what essentially you are doing is you are fixing this input energy and converting it into another form of energy. Now, if you see the definition of the transducer, what you have done is you have taken any useful energy. I am not defining the type of energy, but for the actuator, I am fixing the type of energy, which is electrical in nature. Okay, and transducer defines that it is another form of energy, and this another form of energy is of course not defined for actuator, and it remains another form of energy. So if you see this definition of actuator, then it also fits as a subset of a transducer. So in principle, you are right that sensor and actuator can be considered as a subset of a transducer. Fine. So I hope that the question is clear to you. Okay. Now let us take another question, which is, how does a relative and absolute sensor works? Okay, and we'll see this with, of course, with one example. Okay, we'll try to see some more example if the time permits. Okay, so if you remember, we have done classification of sensors in our first module, where we have classified them on the basis of transfer function that we can obtain from a transducer function that is available in the sensor. We have also classified them based on the energy that it utilizes. We have also defined based on the selected reference. Okay, based on the transducer function, we have defined it as a direct sensor which converts any useful energy to electrical energy. Okay, but then we have seen that there are cases where you do not have a sensor which can convert one form of energy to to electrical energy, and that form of energy is available with us. For example, say I have a sensor whose input is, say, heat energy. Okay, whose input is the heat energy, but the stimulus that I have is in the form of a chemical energy. Okay, so for these kind of cases, what we need is we need a transducer which can convert say this chemical energy to heat energy, and this heat energy can be input to a sensor, and then it can convert it into electrical energy. So basically, this complex sensor works in a form of in conjugation with other transducers. Okay, based on energy, we have seen active sensors and passive sensors, where the passive sensors were not requiring any external biasing, while for active sensor you required any external bias, right? The question came from the third kind of the classification, which is based on selected reference, and we discussed that there are two type of sensors based on this, and that is absolute and relative sensors. Okay, so we defined an absolute sensor as a sensor which detects a stimulus in reference to an absolute physical scale. Okay, and this I hope that the confusion is because of the absolute physical scale. Okay, so if we can define this absolute physical scale, I hope I think that the confusion will be I think confusion will be cleared. Okay, so this absolute physical scale that I'm talking about is a fixed and well-defined reference. Okay, this well-defined reference can be in case of say pressure, it can be it can be say a vacuum. Okay, because it is a fixed physical parameter, you cannot change it. Okay, you can have a reference as an absolute zero, or in electrical connection you can have a true ground. Okay, so these parameter, if you see this physical scale remains fixed. Okay, and these are well defined references. Okay, however, a relative sensor measures stimulus relative to the surrounding ambient. If you see in this case, in the case of absolute sensor, your surrounding is almost fixed, it doesn't change with the surrounding. But here you have the relative sensor measuring a stimulus with relative to the surrounding ambient. It means the reference point is changing. It has a baseline, and on the baseline it is measuring something, or there is certain initial condition. Okay, the output is compared. I mean, the output will be when you have output from these sensors, it is taking care of the initial condition. However, in this case, in the case of absolute sensor, you do not have any initial or final condition. Whatever measurement is, it is the absolute measurement. Okay, so a good example of absolute and reference sensor are a pressure sensor. Okay, so pressure sensor can be a very good example to understand this absolute and reference sensors. Okay, if I talk about an absolute pressure sensor, the absolute pressure sensor produces signal in reference to a say vacuum. Okay, or an absolute zero on a pressure scale. Okay, so you are measuring pressure with respect to vacuum. Okay, so you don't, this vacuum is not changing with the surrounding. Okay, if you put this in any vacuum condition, it will be always vacuum. So you have a absolute zero on a pressure scale, and this this absolute pressure sensor produces the output with respect to the vacuum. So it can be considered as a absolute pressure sensor. If I talk about a relative pressure sensor produces signal with respect to a selected baseline. Okay, this selected baseline is of course a not zero pressure condition, like we have discussed the pressure sensor in other modules. If you have not studied, you will be definitely studying that. Okay, a not zero pressure sensor can be a not vacuum condition, like it can be a atmospheric pressure. Okay, so your pressure sensor now again giving output in terms of you are trying to measure the pressure, but now it is measuring in terms of the atmospheric pressure, not with respect to so not with respect to the surrounding. Okay, or not with respect to the vacuum that we talked in the absolute pressure sensor. Fine. Okay. Now, I hope that this concept of absolute and reference sensors are clear. There can be more example of this, like in terms of say temperature sensor. Like for example, if you talk about a RTD sensor, okay, or a thermistor. Thermistor is a kind of absolute sensor. Okay, while the thermocouple you measure temperature with respect to this hot and cold junctions. Okay, and that's why it is not an absolute pressure sensor, but absolute temperature sensor, but a relative temperature sensor. Okay, there can be a number of examples. Okay, for this relative and absolute sensors. Okay, then one more question that I would like to discuss and that came and we have discussed that in very brief in our course is what is meant by a chemical sensor? Okay, this was one of the question that that arises, and the idea is very simple. If your sensor is detecting, we'll define it, of course, but if your sensor is defining or detecting certain chemical species or chemical analyte, the sensor is simply called as a chemical sensor. Okay, there are different parts of this chemical sensor we'll see, but if it is measuring certain physical parameter like a touch, okay, or a sight or a hearing. Okay, these are all the sensors which deal with all these are physical sensor. Of course, these are all inspired by nature only. Okay, like if you smell something, okay, some analyte, okay, we taste something. Okay, so the analyte comes in contact with our tongue, and then we sense that okay, this is this particular item. Okay, so this kind of artificial devices are known as chemical sensors. Okay, if I define it more scientifically, I can say that a chemical sensor is a device which consists of a receptor that interacts selectively with the target analyte. The target analyte is mostly the chemicals that I want to detect. I will talk about some of the analyte. Okay, and we'll have a transducer which converts the chemical interaction into a electrically measurable signal. Okay, so this is how you define a chemical signal. Okay, if you add more detail on this, the measurable signal should be compatible with the interface circuit that we have and other things. So two crucial parts is the interface. Two crucial parts are receptors and the transducer, and third crucial part for this chemical sensors are the electrical circuit. Okay, on which it is built up. Okay, there can be different type of chemical sensors, and mostly these are in terms of some liquid, certain solids, and certain vapors. If you talk about some vapor-based chemical sensor, you have the most beautiful example can be a gas sensor, which detects gases in the environment. So gas sensor is a typical example of a chemical sensor. So although if you see, oxygen is not a reactive species. Okay, you cannot say that it is. In ambient it is just available. Say you have nitrogen available in the ambient. It is not reacting. But if you have a device which is detecting nitrogen, you have to call it nitrogen sensor, because it is nitrogen is a kind of chemical that so the definition comes from the species that I am trying to detect. Okay, not the kind of device. The principle of detection can be anything. It can be optical, it can be resistive, it can be capacitive, etc. But the species remains a chemical. Okay, so you can have gas sensor based on different transduction techniques to detect gases like oxygen, carbon monoxide, dioxide, ammonia, H2S, hydrogen, nitrogen oxides. Okay, sulfur oxides, methane, and other volatile organic compounds. Sometimes volatile organic compounds are also segregated, like methane and others. So of course they all are called the chemical sensor. Okay, you can have ion sensors. Okay, so it detects specific ions mostly in the liquid. Okay, and your sensors are mostly ion selective electrodes, mostly electrochemical kind of device or SFET kind of device. Okay. It detects, say, for example, pH. Okay, pH is nothing, that it's a H positive ions. Okay, so a pH sensor is a good example of a chemical sensor. Okay, although it falls under ion sensor, but ion sensor itself is a type of chemical sensor. Okay, then you can have ion selective sensors for detection of say sodium, potassium, calcium, etc. Similarly, you have sensors for detection of fluoride, chloride, nitrates, etc. Okay. Similarly, for heavy metal ions, you have lead detectors, mercury detectors, cadmium detectors. All this falls under ion sensor, which is a kind of chemical sensor. Okay. Then you have toxic and pollutant sensors like detection of pesticides, explosives, different pollutants in terms of say aromatic pollutants like benzene, formaldehydes. Okay, then you have heavy metal detectors in soil, in water, etc. Okay, and then although alcohol falls under VOC, ethanol is a kind of volatile organic compound, but then people has developed it under different heads also, like you have a breathe analyzer. So they sometimes are classified as different altogether different class of device. Okay, then you have drug sensors to detect different solid drugs also, but again mostly based on the vapors which are being emitted from this, like cocaine. Okay, they are very helpful for medical applications and forensic applications. Okay, I hope that the definition of chemical sensors are clear to you. Okay. So let us talk about another question, which is based on Miller indices. So the question exactly is Miller indices are difficult for the student to understand. Okay, so it's not the truth. Okay, Miller indices are not that difficult, and I hope that the concept of Miller indices arised when we talked about different kind of wafers, like 100, 110, 111, that kind of wafers, and these all are different planes. Okay, and here only we talked about I think about the Miller indices. Okay, so let us quickly see what is Miller indices. I hope that in today's class it will be clear to you that what Miller indices is all about. Okay, so these all we discussed, of course, when we talked about this wafer. We talked about like silicon, single crystal silicon is available, and depending on what plane it is helpful for doping. Its resistivity varies, the etching rate varies, deposition rate varies, etc. Okay, so mathematically we'll see what is Miller indices, but theoretically it is defined as a set of three small integers, HKL, that describes the orientation of a crystal plane with respect to the crystallographic axis. Okay, they are obtained by taking the reciprocals of fractional intercepts that the plane makes with the crystal axis and reducing them to a whole number. Okay, so this reduction after when you reduce it in terms of whole number, actually that denotes Miller indices. Okay, so let us understand this with one example. Okay, consider that a plane is making an intercept of say 2 on the x-axis. Okay, 1 on the y-axis, and again 2 on the z-axis. Okay, so let me take the pen. Okay, now you have intercepts 2, 1, 2. So on x you have 2, y you have 1, and at the z plane you have 2. Okay, so the definition of Miller indices is they are obtained by taking the reciprocal of the intercepts. Okay, so if I take the reciprocal of this, I have 1 by 2 of x. Okay, then 1 by 1, which is again 1. Okay, and again 1 by 2, which is written over here. Okay, so 1 by 2 on x-axis, if I am taking the reciprocal of intercept, please listen it carefully, and 1 by 1, which is 1 on the y-axis, and again the intercept is 2, so the reciprocal is 1 by 2. Okay, now you take this 2 term common among the reciprocal. Okay, so now you have 1 by 2 will multiply with the highest denominator to all these reciprocals. Okay, the highest denominator is 2. Okay, so I will multiply it with 2. Okay, I will also multiply this with 2. I will also multiply this with 2. Now I have a value. This get cancelled. This get cancelled, and I have a value. This 2 will remain. So I have 1, 2, 1. Okay, this is my Miller indices, and this is how a plane is defined. Okay, now if you see here in the intercept, you were mentioning a comma. Okay, please note that this comma is not available in the Miller indices. Okay, you denote it without any comma. Okay, let's see one more example with a different intercept. Say 2 at the x-axis. Okay, right? 2 at the x-axis. Say 4 at the y-axis, and say 1. This is my plane now. Okay. Now this is in the second case. Let me take a different color. Okay, for the second case. Fine. This is my plane. Okay. The intercepts are 2, 4, and 1. Okay. To calculate the Miller indices, what I will do, I will just take the reciprocal, right, and multiply with the highest denominator. Okay, so I will multiply it with 4. I will multiply it with 4, and I will also multiply this with 4. Okay, so I have 2, 1, and 4. 2, 1, and 4. Okay, now if I don't put any comma, this will be my Miller indices. Okay, this Miller indices is very, very important. Sometime if your plane is parallel to certain axes. Okay, so consider a case of intercept 1, infinity, infinity. What it means is the plane is cutting the x-axis at 1. It is making an intercept of 1, and it is parallel to the y and z axes. Now, if you take this in the calculations, say for example, reciprocal vector calculation and others, okay, it will be very difficult to carry this infinite term there. Okay, and most of the terminology will be infinity if you keep on multiplying with this. Okay, so what people thought to convert this in terms of Miller indices, and then if you convert this into Miller indices, say for this example, 1 infinity, infinity, you have 1 by 1, 1 by infinity, and 1 by infinity, right? So in such cases, you have a Miller indices 1, 0, and 0. Right? So you multiply this all with 1. Okay. So you get 1, 0, and 0. Okay. Now for the reciprocal 1, infinity, infinity, you have a reciprocal of 1, 0, 0. And this is the Miller indices for intercept like this. Okay, so I hope that the concept of Miller indices is pretty clear to you. Okay, fine. Then there was a question that while deriving the expression for the peak voltage of the pyroelectric sensor, the expression is given as permittivity over thickness. However, the other way, I'm getting other way around. What the student mean? Okay, kindly verify which one is correct. Okay, let me take the pointer. Okay, kindly verify which one is correct. I have attached the derivation for your reference. Okay, so if you remember, we talked about pyroelectric material. I think till now everyone has got this. Okay, the pyroelectric materials were the crystalline substances which can generate electrical charge when exposed to a heat flow. Okay, and in the pyroelectric discussion, we have seen two pyroelectric coefficients. One was pyroelectric charge sensor, which we defined as dps by dt, where ps was the spontaneous polarization, and we also defined another coefficient, which was the pyroelectric voltage coefficient, which is de by dt, where E was the electric field strength, right? And then we calculated this PQ by PV as epsilon R into epsilon naught, okay? And we talked about charge and voltage changes that can be described as delta Q as PQ A delta T and del V as PV H into delta T, okay? And we recalled the C value, and the C value was del Q by del V, and from this equation we have found that this del Q by del V we have already calculated as epsilon R epsilon naught A by H, right? This was the value, and what we did is actually in this equation, in the equation of del V, this was the this was the del V equation. What we tried to do is we tried to replace this value of just a minute. Del V, we have already seen that PV into H into del T. Okay, so if I replace this H, H value from this equation can be epsilon R epsilon naught A by C, right? Right? And then we put this and we found that this is H by epsilon R into epsilon naught and not the other way around, right? Which was the older expression where I have written, I think, epsilon R epsilon naught H by. So if you calculate this, even if you derive it, you get this particular value. Okay, so I have attached this here, and also it is corrected in the slide. Okay, so I hope that now, of course, with this, our the takeaway from points also changes. We have now it is seen that the peak output voltage is proportional to the sensor temperature rise, proportional to the pyroelectric charge coefficient, proportional to the thickness, and inversely proportional to the dielectric constant. And earlier it was directly proportional to the dielectric constant. So that was an error that is now fixed. So other questions that I have seen, like week 3 assignment, and other things, we have now changed the answer from D to C. It is now increasing the dielectric constant, right? With this, I think that those who has given the correct answer, that is being changed parallelly. Okay, so this was the week 8 assignment. Okay, so this is now, I hope that it is clear to you. So these were the questions that we plan to discuss. We'll see if there are some more questions, and accordingly we'll see. Okay. So there is one question, could you please tell, which is missing, what we should prepare for the final exam? Okay, final exam, I will suggest that there are 12 different modules. Okay, so I will suggest that you give equal weightage to all the modules. It is not that this particular module is important or that particular module is important. It's not like that. Each and every module starting from module 1 is pretty important in this course, because if you do not understand, say, module 1, it will be very difficult for you to grasp, say, module 5 or module 6, because that is the base. Similarly, module 2, is also equally important, because the characteristics, for example, you are considering in all the sensors that we have seen. Of course, for accelerometer, we have seen some more characteristics, but the fundamentals remain same. All right. So the only tip that I can give you for the final exam is give equal time to all the modules and prepare accordingly. I hope that it will be helpful. Okay. So fine. Then if we do not have the question is, how can I do revision? Just 1 second. Yeah, so there was some question on revision. Yeah, just a minute. How can I do revision for final exam day by day? So the idea is pretty simple. This is a philosophical question. So the idea is pretty simple, that the modules are clearly divided into different lectures. So you have, so what you can do is, say, if you are going through module 3, do not forget to revise weekly, say module 1 and module 2. If you are in module 5, please do not, forget to revise, say module 1 to module 4 in that particular week. Okay, so you can keep on advancing, but keep on revising on the same course. Okay, so that will be helpful, and it will not pile up. Okay, so I hope that we could answer all of your questions, and what we will do is we will meet again next month. You can post your questions like you have done. Okay, and we will try to minimize any mathematical error or other things. Okay.